Hey classes, welcome back. A lot going on today. I wanted to give a quick recap, quick preview of where we're going tomorrow, and a little bit about the board behind me. This is what was the news about noon today. Came to the desk and saw this on my news feed, and I'm going to start with that because one of the things that I always try and emphasize in this class is current events. I know Mr. Westbrook across the hall uses CNN 10 quite a bit. I always use some current events as well. It's important because I started the year with a John Muir quote about how if you touch anything in nature, you'll find it connected to everything else. And one of the things that we actually learn about, so I only talk about things that are germane to the class in terms of things that we end up using later on. And this right here is a big deal in terms of, well, a number of things, not only being, of course, an icon in Britain for decades, but when you talk about Queen Elizabeth and Great Britain, we learn a lot about what was going on in England, particularly as World War II came on. We learn a little bit about World War II in this class because at the end of World War II, in 1945, they kicked off what we call the atomic age or the nuclear age. And we're going to find out how something that big, some uranium and plutonium that was just a little bit bigger than this tennis ball right here, it was possible to make an atomic bomb that devastated an entire city. That really changed everything. How do you get so much energy out of something so small? We started the year about learning about the fundamental forces of nature, particularly the strong force will come into play next week when we learn about the atom, we learn about molecules, how atoms are put together, what's inside of an atom, and how when you fuse or break an atom, either one, you can get a tremendous amount of energy from a very small mass. That's one of the things that we end up talking about. And of course, Queen Elizabeth was queen not until the 1950s, but she was a teenager in World War II when the Nazi Germany was on the verge of taking over Great Britain. And that's a very big deal to know about because you're talking about the United States getting involved in World War II in 1941, but by this time, Great Britain had already been under assault. You're talking about a country that many people thought was going to fall almost immediately to Nazi Germany, and they didn't. They ended up famously rallied by Winston Churchill, not surrendering, but repelling what many people assumed would have just been a very quick defeat for England. So it's a very big deal. We learn a lot about World War II later on when we go into plutonium, uranium, and the background there. Today, we talked a little bit about density. This will feed into our pointing across the room at a periodic table right now. This will feed into our understanding a little bit. And we're not going into too much detail, but we do have to know enough about the periodic table to look for trends. And our lab tomorrow, which I had the students write down on the far side of the board, but we're not getting to those notes until tomorrow, will be to get, let me grab this, the density of water, filling up this and finding out how much, if you have, for example, 500 milliliters of water, what will be the mass of that, and hopefully we'll relearn one of the things that was just a note on the board earlier, but the point of doing the lab and also playing with different volumes is to find out that the density of water is 1 gram per cubic centimeter or 1 gram per milliliter, which of course is the same thing. So we want to talk about why the metric system does that. They make it very convenient for people when they're trying to convert between the units. In class today, one of the things that we started to do was we went out with one of the classes and checked out the shadows. We want to make a prediction. What do you think, based on what you know right now, make a guess, a good educated guess, but a guess, on what will the shadows look like if you measure them at the same exact place and time in another week or two. Are the shadows right now getting longer? Are they getting shorter? Or are they staying the same length? And so that's a big deal. We're looking for trends there too. And in terms of looking for trends, this was one of the in-class assignments that I wanted everyone to, obviously complete, but really start interpreting the data. Let me pull out the old whiteboard here and show you where we're going with this. If you're in class today, if you're looking at the homework that we're going to be doing with this over the next week. Remember, good old Hubble came along and found that for the most part, when you are graphing distance versus time, distance versus speed on galaxies, for the most part, the galaxies, as they increased in distance, were moving away from us faster and faster. This was a huge piece of evidence for an expanding universe. Now, on the smaller scale, I say smaller scale, you're talking, for example, the Andromeda Galaxy. The Andromeda Galaxy and the Milky Way galaxy are coming towards each other right now. They're set to merge in about 4 billion years. But you're talking about galaxy clusters all moving apart from each other. And that led to the evidence that, hey, if you run that clock backward, things must have been all together at the same place at the same time. Now, today we're looking for a little hiccup in the data. We're looking for something that doesn't quite fit the pattern. We are graphing, if you saw the previous board, this is the distance that a planet is from the sun, and we're including Pluto today just to get an extra data point. So Pluto, just like in the old days, is a planet again, just for today in class. If you look at the surface temperature over here of the planet, we're looking for a trend. And if you look at the average surface temperature of the planets, in general, as you get farther and farther from the sun, and you would expect this, it's like being farther from a campfire, the temperature, as the distance increases from the sun, the temperature tends to drop. And that's expected up to a point, but around here, and depending on the scale, I was challenging students to figure out the scale, there's a little hiccup where all of a sudden you've got the planet Venus having a tremendously high surface temperature. It's just a little bit closer to the sun than the Earth. We're 93, I'm going to use imperial units here, we're 93 million miles from the Earth. You're talking around 70 million miles away from the sun. And yet Venus is, on an average day, about 900 degrees Fahrenheit. I'm using imperial units because that would be like taking your average household oven, turning it as high as it would go, and then doubling that temperature. You're talking a temperature that seems way out of step with it just being a little bit closer to the sun. And it turns out that the discovery that Venus was so hot was a huge deal when we're trying to talk about climate change later on in this class. Venus has an atmosphere that traps most of the solar radiation that hits the surface on Earth. It gets reflected back into space. Venus has a lot of interesting characteristics in terms of it's got a backward rotation from the other planets as it goes around the sun. But most importantly for us right now, we're trying to look at the little hiccup in the data. Why? When scientists find something like that, when they're getting what is sort of expected data, and then all of a sudden there's a little hiccup like that, an outlier, something that doesn't seem to follow the trend, those are the places where discoveries are made. Those are the things that like, wait a second, there's something going on here. And in the case of Venus, it turned out that where some people at first imagined Venus, because it was covered in clouds, as being sort of a water world that was raining all the time. I remember in school at one point or another reading All Summer in a Day. You might have read that short story yourself, where there were colonies on Venus and it was raining all the time. It turns out, far from there being, rainforests and oceans on Venus, instead, the average day is raining sulfuric acid and it's about 900 degrees Fahrenheit. And you learn things like that when you look for the hiccups in the data, or you look for something that doesn't quite fit the pattern. Again, this is for tomorrow. It says Friday up there. This will be on the board again tomorrow. After the first period class, it was apparent we weren't going to get this far today. But the first thing we're going to do is we're going to be measuring a volume of water, be different for different classes, figuring out the weight or the mass of the water, and when they figure out the weight of the water, we're going to take it from there. So that's where I'm going to leave it today. Have yourself a good day. I'll talk to you in a little bit. Bye-bye.